Okay, let's start then. Okay, so we have been looking at transmission lines. So we observe that if you have a transmission line, at any point on the line, you can think of the voltage to be composed of a component that is traveling forward and another component that is reflected. So the total voltage is sum of these two guys. And similarly, what is the total current? Minus E minus by Z1, right? And also last class we saw that if you have a short circuit on one end of the line, looking into the other end, how does the input impedance look like at low frequencies? At DC, yeah, it's short. At low frequencies, I mean at close enough, yeah, it behaves like an inductor, so it actually does something like this. And this has multiple resonances. Okay? And similarly, if you have an open circuited line, again at DC it behaves like a pure open, and again you have these multiple resonances. Also, if you take the line here and terminate it with some impedance ZL, and at the end of the line, if the forward voltage is V plus and the reflected voltage is V minus, what is the relation between V minus and V plus? Yeah, it's some gamma L times V plus. And what is gamma L? It's a reflection coefficient. This is this, right? And we saw that if you take the line here and if you make ZL to be Z0 of the line, then the reflection coefficient becomes 0. And what about the input impedance? That's also Z0, right? And that made sense because the load here is saying that the ratio of the total voltage to the total current must be Z0, and on the line this condition is just satisfied only by the forward component, so nothing gets reflected back. So at any point on the line, the total voltage will be only the forward component and the total current will be only the will be only the forward current. So the impedance at any point on the line is Z0. So this means, let's say you have some circuit here and you have a transmission line and terminated with Z0. So I know that the looking in impedance here is Z0. So I can simplify the circuit by taking the same network, putting the Z0 right at the end of this network, and if this is Vx and this is Vy, so this voltage will be what? Yeah, what will be this voltage? I mean, this is the network, I am saying I will simplify it. If I compute this voltage, what will it give me? Vx. And to find Vy, I will simply delay it. Right? This will be. Okay. And yeah. Also, we saw that if you take this transmission line with the characteristic impedance Z0 and say you put any load at the end, looking into this end of the line, at t equal to 0 plus, what is the impedance? It is Z0. Again, this makes sense because at 0 plus you only have the forward wave that is launched, so there is nothing that is coming back, so the impedance is Z0. As t tends to infinity, what is Zn? Zn is ZL, right? And that makes sense because at t equal to infinity basically means I apply some step and then look at what happens in steady state, and in steady state this basically behaves like a should. And we saw that, so if you take the source here, which has the source impedance Zs, and you put the transmission line, and you have some ZL here, and if this is U of t, and let's say this is Z0 comma tau. So if I look at this voltage Vx at t equal to 0 plus, what will happen to Vx? Yeah, because at t equal to 0 plus, looking in this Z0, so you just have the division among those two, which is Z0 by Z0 plus Zs, and as t tends to infinity, what happens? So this basically is the short, so we have the division between these two guys. So again, depending on what is higher, I mean, this can be higher or lower, right? Basically what I'm saying is, this can be lower than this also. I'm just taking it. So yeah, this will be the steady state. So if you look at the transient, it will do something like this, right? And this is happening because you have reflections at both ends of the line, right? And what is the reflection coefficient at the load end? That is ZL minus Z0 by ZL plus Z0. This is not equal to 0. And at the source side, what is the reflection coefficient? That is Zs minus. So since both are non-zero, you will have reflections from either ends of the line, and this will happen for infinite number of times till it reaches steady state, right? And if you don't want this infinite reflections to happen, what should I do? Or you either make ZL Z0 or Zs equal to Z0, or make both, right? I mean, either of these will work. If you make ZL equal to Z0, forward wave goes, nothing gets reflected. If you make only this guy as Z0, you will have a forward wave launched that gets reflected, but then it stops. Okay, great. And this, I mean, besides preventing this infinite reflections, this gamma L also signifies something that we kind of looked at it at the end of the class. So let me elaborate that. Say you have a source here, transmission line. See, this is ZL, and let's say source impedance is Z0, so that I don't worry about the reflections at this end. So let's say this is V in. So let's say at the end the forward is V plus and the reflected is V minus. What is the total voltage across the load? V plus plus, V minus. What is the total current flowing into the load? Or I mean, you know the transmission line, right? At the end of the line, whatever the current is, the same current has to flow. What is that current? V plus by Z0, right? I mean, this is the current at this end of the line. The same current is going here. Fine. So what is the total power that is dissipated across ZL? It's a product of the two, so that becomes Z0. Okay. Okay. By the way, so I mean, this is the power dissipated across ZL, right? And it looks like it doesn't have ZL at all. So what's happening?
V minus how?
Right. So how is V minus related to V plus? It's gamma L times V plus, and that gamma L contains Z. That's all. Okay. And let's say this is whatever I have written here are all RMS quantities. Some sinusoidal signal is given, and these are the RMS voltages of the forward and the reflected waves. So then the RMS V minus will be mod gamma L at that frequency times the RMS of the forward wave. Fine. I mean, remember, gamma L can be a complex quantity, right? So if I do this, I'll have, what do I get? PL to be? So I'll have V plus square by Z0 minus mod. Okay. And say this forward wave is V plus, and let's say this is in Laplace domain. So what about the forward wave at this end of the line in Laplace domain? Yeah, so what is the Laplace? E power s tau. And similarly here it is e power minus s tau. Okay. And when you apply an input at t equal to 0 plus, let us say, so only the forward wave is launched, right? And what is the forward, the forward wave here is v plus of s e power s tau, right? And when you apply the input, what is the, at t equal to 0 plus, the looking in impedance is z0. So what will be this guy? Vn of s by 2. Fine. At t equal to 0 plus, the looking in is impedance is z0. So the forward wave will be basically the division between the two impedances, that's basically half. Okay. So basically that goes and gets reflected and comes back, but then no other reflection happens. Is that fine? So the forward component is simply this guy. Whatever forward wave was launched, when you applied the input, that's what is the forward component at this end, right? And you will have one reflection at this end, but after that there is no other reflection happening. Is that clear? So what is v plus of s? Vn of s by 2 e power minus s tau. So if I call the RMS of the input to be some Vn, what is the RMS of the forward wave? This is the Laplace domain, right? I'm saying, let's say the input has an RMS of Vn. What will be the RMS of the forward wave? Come on, people. What is, if I, v plus of t is what? Vn of, from this, what can you say about v plus of t? By 2. Is that fine? So I'm saying if this has some RMS of some Vn, what will be the RMS of this? Half, right? So this is going to be Vn square by 4z0, fine, into 1 minus gamma L square. Is that okay? Right? So now if you look at it, it looks like we are actually trying to deliver this power Vn square by 4z0 through the forward wave, right? And this reaches here, but because ZL is not equal to Z0, this entire power is not getting delivered to our load, right? A fraction of the voltage gets reflected, so the power that is dissipated in ZL is smaller than this. Smaller than Vn square by 4z0. Okay? So if I were to make sure that this entire power is delivered to ZL, what should gamma L be? 0, right? So only if ZL is equal to Z0, the power dissipated will be this guy. Okay, and that is why that is another reason why you want to have gamma L to be as small as possible, right? Is that okay? So have you seen this kind of something similar in some other scenario?
Yes.
This is basically the maximum power transfer, right? So let's say you have a lumped network, say this is V, and say this is some RS, and say RL, right? What is the power dissipated across RL? What is the current flowing through RL? RS plus RL. So power is I square times R, right? You can actually find that this, you can write it as Vn square by 4 RS times 1 minus some gamma L square, where gamma L you can define to be this. Okay, it's not very difficult, right? You can simplify it. So this, if I simplify it, what do I get? Vn square by 4 RS times L 1 plus gamma L times 1 minus gamma L. So what is 1 plus gamma L? What is this? Gamma L is this. What is 1 plus of this? Yeah, 2 RL by RL plus RS. And what is 1 minus gamma L? 2 RS by RL plus RS. So you take this by out, 4, 4, and RS goes off. So we end up with V in by RS plus RL the whole square times RL. And that's basically the power we have, right? Okay. And I mean, of course, you know that to have maximum power transfer, the condition was RL equal to RS. Right? I mean, this whatever we saw for transmission line is basically the same thing, just told in a slightly different way. So it's the same result. You are relearning it in a different scenario. That's it. But the underlying principle is same. Is that okay? Cool. And yeah, this idea of delivering the maximum power to the load is very crucial, especially in RF designs, because say your entire RF receiver you can make it in one chip, but finally you need to have an antenna that will be an off-chip component that will be fabricated separately. And I mean, you can think of antenna as another transmission line that is picking up signal from space, right? That's all. So again, this will be designed to have a characteristic impedance of 50 ohms. So let's say you will connect it through 50 ohm cable and connect it to this. And let's say the input of the receiver will mostly be a MOSFET, something like this. So what is it looking in impedance? Yeah, I mean, in practice we'll have a capacitor, right? So now you see that because of the fact that gamma L is not zero, whatever power you are picking from the antenna, it's not actually getting delivered to your receiver. Okay. So you need to make sure that looking in matches the characteristic impedance Z0. So what is one brute force way to ensure this? Yeah, one brute force way is to put an R equal to Z0 here.
Low, at that frequency it should be very low, because the parallel combination of R and C should...
Yeah, I mean, let's say this capacitor is small, right? I mean, I added the capacitor because you told infinity. Compared to infinity, the capacitor will offer something. Okay. So this is obviously one brute force way, but of course this is not preferred because the moment you add a resistor, yeah, noise, not gain, right? It will start adding noise, and already you are trying to pick up some microwatt and picowatts of power from antenna, so you don't want to add too much of noise. Okay. So I mean, there are techniques so that if you add something here, the looking in impedance looks close enough to Z0, but for a narrow band of frequencies. And that's okay because you are anyways trying to receive a narrow band of frequencies in radio receivers. So as long as you ensure that the looking in impedance is roughly Z0 for a narrow band of frequencies, then this will work. Okay. And in this course, of course, we saw that the recent trend is to have LPDB based circuits as the RF front end, right? So this, of course, is a passive mixer. And of course, we saw that in practice we'll have in-phase and quadrature components. So we'll have a double balanced IQ mixer like this. This is the single-ended version, and the differential version you will do something like this. Okay. And this will be 50, 5180 and so on. I'm not writing the phases. Okay. So basically the differential input applied here will be down converted across these capacitors. Now let's say I add a resistor here, RS, and apply the input here, and if I take the output here, what is the function? What will this do? This is basically the 4-path bandpass filter just connected in a differential fashion, right? This is basically single-ended case, you see it's just a 4-path bandpass filter, right? And this was a differential implementation we had. So you apply the input here. At this end, the signal is bandpass filtered, and the bandpass filtered signal is then demodulated, or it's down converted, and is available across the capacitors. Right? This is basically one possible way of having an RF front end. So we can basically connect it to your antenna here like this. but now you see that the looking in impedance is no longer an LTI impedance, right? You have a periodically varying impedance, right? So if I were to model it, I will have some input source, say some transmission line with Z0, and then I have some impedance that varies with them. Okay, so we saw this notion of reflection coefficient with respect to LTI impedances. So I mean, basically for the LTI network, we had a forward wave V plus, reflected wave V minus. So now we have an LPTV case. So how do you think we'll proceed? Why adjoint? Adjoint is not the solution for everything. I mean, the question is simple, right? What I'm saying is, we learned something for LTI network, and then I see that, yeah, I encounter, time varying, periodically time varying elements. Will I say that I don't know anything, or is there some trick? Yeah, we'll treat, instead of forward wave to be a V plus, this will be a vector of V plus and V minus, right? And this transmission line will have a characteristic impedance matrix, and this is not time varying, right? So what will be Z0 matrix? How will it look like? It's a diagonal matrix with only Z0 here. And this you will replace it by, say, an admittance matrix YL, and let's say call this Y0 to be Z0 inverse. Okay. So at the end of the line you will have a forward wave, but that's now a vector. Similarly, a reflected wave, which is again a vector. So we'll do the same thing, right? So we know that the currents here are equal. So current at the end of the line, what is it? At the end of the line, what is the current? Y0 bar into
V plus Z minus
V minus. Fine. For LTI, this was basically V plus by Z0 minus V minus by Z0. So here you will write it in matrix notation like this. And this current is basically the current flowing into the load. So that is YL times the total voltage. Is this. So what is the relation I get for V minus and V plus? So we'll have V minus times Y0 plus YL to be YL minus Y0 times V plus. This is all matrix and vectors. So V minus will be Y0 plus YL inverse times YL minus Y0 times C plus. Okay. So now basically you have a reflection coefficient matrix instead of a single number. Right? So gamma L, which was a single number for LTI case, is now a matrix. And that makes sense because now you'll have multiple frequencies and you'll have frequency translations, right? So if you feed in signal at some frequency, the power will not be delivered only at that frequency. You'll also have power delivered to the load at Fs, multiples of Fs plus the input frequency. Is that okay? Okay, so now let's get back to transmission lines. So let's say you have a two-port network and this is a linear two-port. Okay. Say the port voltage here is V1 and the current is I1. Here the voltage is V2, current is I2. Now say I am interested only in the terminal behavior of this two-port network. That is, I don't care what is inside the network. I just want to know at these two ports, if I apply some input, how the other port behaves. So how do you characterize such a two-port network? Huh? What did you say? Yeah, basically you have learned all these parameters, right? So the notion was simple, right? You had four variables, V1, V2, I1, I2. You have to you choose two of them to be independent, two of them to be dependent. So you have 4C2, which is 6 possible combinations, and that's why you have Z, Y, whatever G, H, A, B, C, D, or something. 6 possible parameters. Okay. So let's say you take Y parameter. So what are the independent variables or the dependent variables in Y parameters? You choose the currents to be the dependent, right? Yeah. And this will be a function of the voltages. So it's a linear two port. So this will be a linear combination of this, right? Okay. So what is Y11? V2 is 0. Okay. So what is Y21? When V2 is 0. Similarly, Y12 is I1 by V2 when V1 is 0, and Y22 is this guy. Okay. Cool. So let me actually take this guy. So let's say you want to find these two guys. What do I have to do? I'll have to apply input at the first port, short the second port, right? So I'll take the two port, apply some signal V1, short this guy, and to find these two parameters, what is the input? I should apply the voltage at the second port and short the first port. Okay. This is V2. So now look at these parameters and the networks here, and tell me if you can find a relation among them under some conditions. Okay. I mean, let's say this contains only RLC, linear RLC. I know that if I apply a voltage here and measure a current in this direction, the same transfer function I will get when you apply the voltage here and measure the current in this direction, right? So what is this? This is basically I2 by V1 when V2 is 0. What is that? Why V2? What parameter is this? Y21, right? Right, and this guy is what? I am finding the current here, I1 by V2, that's Y1. Okay, so these two are equal. Yeah, that basically comes out of reciprocity, right? So if you have a linear RLC, it is a network containing only linear RLCs. How many parameters do you need? Not parameters. How many variables you need to characterize it? No, Y parameters required 4, right? Now you know a relation between them, so you need basically how many? 3 of them. So I can just say Y11, Y21, Y21. So by just by knowing 3 parameters, I can characterize the entire two-port network. Okay, and similarly, if you choose other sets of parameters, you will have some relation between some 2 parameters. And of course, you can find it using the reciprocity results. Cool. So now this is all nice and good on paper, but let's say you go to lab and try to measure it. Okay. And by the way, why are these two-port networks useful? Why are you learning? I mean, all these Y parameters, Z parameters. Why? Okay. Can you elaborate a bit more? Why? I mean, let's say. Sorry? We can measure that. No, I mean, let's say what I'm saying is this network. If you have, let's say it might have 100 transistors. I can take.
At small frequencies, we can characterize the whole system to these bunch of matrices, and then we compute.
Okay, I have the network, so why do I need the parameters? I have the entire network with me, made of say 100, 200 transistors. No, let's say, this is also linear, right? Assume that the network is also linear for small signals.
It's a big circuit, then to simulate the big circuit and stuff.
Exactly, right? I mean, this circuit can have 1000 transistors. It might have, I mean, it will take a lot of time to simulate. And when you are trying to build a big system, you will have say several of such small systems, each made of hundreds and 200s of transistors. So now we want to see how when you put all these small systems together, the overall system behaves, right? So instead of taking the entire circuit for each of the network, if you know what is the two-port parameters, you can actually use them to model that subsystem, and using those two-port parameters you can simulate the entire system, right? This is going to be much faster than taking the complete transistor level implementation of each subsystem, right? That makes sense, right? Okay. So yeah, that is why you want to actually have this two-port characterization. And let us say you have some small subsystem made into an IC. You want to characterize its Y parameters. So what will you do? You will basically try to put it on a PCB. And let's say these are the 2 ports. And let's say you want to find Y11. What do you have to do? Apply the input on port 1, short the port 2, and measure the current flowing in the second port. So I'll have to apply some signal here. So in the lab you will have bulky signal generators, and then you will have connections like this. And the second port has to be shorted, but you also have to measure the current flowing in that. So we'll have some measuring device here. So we'll have a cable running like this, right? I mean, this is just practical difficulty, right? You can't directly, short here and measure the current. This chip is going to be very small, of the order of few millimeters maximum.
We can use op-amp and virtually short and pass that current through the resistance.
Which one? But I need to measure it, right? How do I measure it? I need some equipment, isn't it?
It will create voltage around that feedback resistance.
But I have to short this guy, right?
You will short what means.
No. See, virtual short is different. What is virtual short? It says that 2 voltages are equal without actually shorting them. But here I actually have to short them. Okay. So this is how the setup is going to look like.
For why don't we need to measure the current in that same port 1?
Oh, sorry, Y21. Sorry. Fine. Yeah. Right. I mean, yeah. Finally, you are measuring. You will measure all 4 parameters. So this is the setup you will have. Okay. So now you have learned, right? If you have long cables, you no longer can treat them as a simple short. So what is that? You have a transmission line, right? So if I had to model this is the chip, right? The 2-port here, and then these cables are basically transmission lines. And similarly here I'll have transmission line, and here is when I'm shorting it, right? I mean, also please remember, when I draw 2 cables like this, in practice you don't have 2 cables, it's just 1 cable where you have inner and outer conductor, right? Okay, great. So now let's say if you do this, we know that if you have a transmission line and you short circuit on one end, what will be the input impedance? How will it look like across frequencies? It is going to have multiple resonances, right? So you will, basically you want to characterize this Y parameters for all sets of frequencies, but you see that the moment you make this setup, looking in is not a short anymore. Only at DC it is exactly short, at low frequencies okay, and at high frequencies no way, right? So first problem is that because you have these long cables, a short circuit is not going to behave like a short circuit at this end. Same holds good for the open circuit also, right? And also say you apply some input, some voltage appears here, and if you think about it, looking in impedance has multiple resonances, right? Say you are measuring this parameter close to one resonant frequency, then this sees like the gain from here to here is going to be what? Yeah, it's going to be extremely large, right? So from here to here you will have a large gain. So that wave goes here, gets reflected back, but some portion of it will also get leaked to the input, right? I mean, amplifier ideally it's supposed to conduct or transmit signal from the input to the output, but in practice, you know, due to the parasitic capacitors, you'll also have a finite leakage into the port 1. So we'll have a small alpha getting coupled there. So this will again go and it will get reflected and come back. It will see a large gain again, and then this goes on in a loop, right? And if this factor alpha times A large is greater than 1, you will have alpha times A large. Second, you will have alpha times A large square plus so on. So will the series converge or diverge? It is going to blow up to infinity, right? If this factor is greater than 1. So if this round trip gain is greater than 1, it is highly possible that the system will become unstable, right? Cool. So these are some of the practical difficulties in actually measuring these parameters, where you want to have short or open on one end of the port. Okay. So now, if you think about it, all these problems are arising because you have multiple reflections back and forth the line, right? It's not behaving like a short circuit because, you know, something goes and comes back, and that's what alters the impedance here. And similarly, this instability is happening because you have infinite reflections. Some signal goes, comes back, and then it keeps going. So to solve this problem, we need to prevent reflections from both ends. So what should I do? Yeah, so what should I do? Yeah, so I mean, tell me what to do, right? So this is the 2 port. Let me show the 2 port here. So they say these are the cables we have.
The output resistance of that block should be equal to Z1.
This way. But that is not under our control, right?
The block is in our control.
No, this is some circuit that you have designed.
Load should be transformed at the end of the transition.
So we put a variable.
I mean, okay, see, you think about it. Something goes here. I don't want that thing to get reflected back.
Load should be transformed to Z0.
No, say this has an impedance Z0. So something will go, but I don't want that to come back.
Yeah, so it
What
should
should I-
appear as Z0.
Yeah, so what can I do here?
Matching network.
So I should put,
Matching network.
no, Z0, right? Why matching network? Nothing.
But eventually there will be some ZL at some end. It should be
Wait.
transformed to Z0. Just that.
No, I mean, this is under your control, right? See, this 2-port network is something you design. You are going to put the cable. What you are going to do here is under your control. So at least it makes sense that if I put Z0, no reflection comes. Fine. Similarly, at this end also you put a source.
Z0.
Z0.
So but what I was saying is that there will be some ZL fixed at some other end, because eventually we have to deliver power.
No. I'm not trying to see. This is only for characterizing this network, right? The whole idea started because he wanted to characterize this 2-port network. He wanted to measure some 2-port parameters for this, right? So this is, the network is floating.
So the input impedance is not 0 as we wanted it to. We wanted a short.
Exactly. So that let's come to that.
Variable load that varies with the frequency, since that it always looks like a short.
Yeah, that is not possible, unfortunately. But this is at least simple. Like what you're saying is absolutely right. Now this no longer is a short. But at least now, if this has a characteristic impedance Z0, and this is Z0, what is the looking in impedance? It is Z0. So it is as if I put a Z0 right at the end of the chip, right? This you couldn't do with short circuits, right? And similarly, here also again looking in, it looks like Z0, as if you have terminated these 2 ends with Z0. Fine. And so now you see that you will have both forward and reflected waves. And similarly here, let's say it's V2 plus V2 minus. So it no longer makes sense to simply talk about voltages and currents. We need to consider both the incident and reflected waves. And the moment you know both of them, You can also find the total voltage and total current at this end. Make sense? And also finally, see this two-port network is something you will design. Okay, and basically this two-port parameters will be measured by some costly equipment. So that will generate the signal, that will have this Z0 here, and then measure the quantities here and here. Okay, basically it will be able to measure signals at these points, right? And these are the cables that you are actually using to connect the equipment to your two-port network, right? Now the equipment, it can measure, let's say it measures the forward voltage at this end of the line. What can I say about the forward voltage at this end? It's a delayed version. So basically what I'm trying to get is that if you know the forward and reverse voltages, that makes things much easier, right? So now you have this two-port network. Again, this is a linear two-port. So these are the things, and you have the cables here. Okay. So let us say this is V1 plus, this is V1 minus. Similarly, this is V2 plus and V2 minus. So now I'll deal with these four variables. So I'll choose two of them to be independent, choose two to be dependent, and let's say I choose the reflected voltages as the dependent variables. That will be a linear function of these guys. Make sense? I mean, logically, see, this reflected voltage will arise because this voltage gets reflected, and also a fraction of V2 plus will come here, right? Same holds good for V2 minus also. So you will represent it as a linear combination, and this is the these are the parameters. So these are called S parameters or scattering parameters, because it looks like as though the waves are incident and it gets scattered in all directions, right? That's the reason they can. Anyways, cool. And remember, here he's told that we'll terminate on either ends with Z0, and Z0 is the characteristic impedance of the cable that you are going to use. Okay, so unlike this Y and Z parameters, the S parameter is not complete unless you specify what is the Z0 that you have used, right? Because this is all assuming that you don't want to have reflections, right? And it all depends on the characteristic impedance of the cables that you are using, right? So with S parameters, you will also specify what is the reference impedance with which you have characterized this parameters. Okay, good. And in practice, it turns out that okay, let's say again, assume that all of them are RMS quantities, V1 plus, V1 minus, everything. What is V1 plus square by Z0? What does it give you? It gives you basically the power of the incident wave, right? And similarly, V minus square by Z0 gives the reflected power, right? So instead of relating V1 plus and V1 minus like this, people often take these quantities, V2 plus by Z0, so V1 minus by Z0, because if you square it, it directly gives the power. Okay, and they call this as, I think, a bit confused, this is A1, A2, V1 and V2. Okay? Really innovative choice for variables, right? Cool. So yeah, this all in practice you will do by square root of Z. But I mean, we'll not consider that because it makes more intuitive sense to look at forward voltages and reflected voltages. Okay, so let's actually look at this once again. So we have this two-port network. have and let me mark this. This is V1 plus, V1 minus. Here this is V2 plus, V2 minus. So how do I find S11? What is S11? I mean, from the equation, what is S11? V1 minus by V1 plus when V2 plus is 0, right? So S11 is V1 minus by V1 plus when V2 plus is 0. So the input must be in the port 1, so I'll apply something like this.
Basically, we want to prevent the reflections at the beginning of the transmission line from the source side. But there will be reflections at the input of the input port.
That we cannot prevent, right? Because this is not under your control. The only thing that is under your control is what are the ends. Okay.
And this Z0 which we are using for the instrument measuring with, that is the reference impedance.
Correct. I mean, this Z0 should match the cable's Z0. Okay. Okay, so this is the deal. So I'll apply the input here, no issues. So I want to make sure V2 plus is 0. So basically, if I apply some input, forward wave goes, something goes here. That should not get reflected. So what should I do? I'll put a Z0 here. Fine. Because if you launch an input, this is going to launch some wave in this direction, and I don't want that to come back. This guy is V2 plus. So if this doesn't, if V2 plus must be 0, this guy must be Z0, right? So I mean, so basically this is V1 minus by V1 plus when V2 plus is 0, or I can just say when I put Z0 at port 2. Okay, and if you think about it, it just says what is the fraction of the incident voltage at port 1 that gets reflected back. So this basically gives the input reflection coefficient. Similarly, what is S21? Same thing, right? So S21 is V2 minus by V1 plus when V2 plus is 0, or again I'll put Z0 at port 2. So same experiment. I need to measure what is V2 minus with respect to V1 plus. So I mean, if you think about it, this is the wave that is being launched. I want to find what reaches the load end. So this is kind of the gain of the system, right? Or the forward gain. So this within quotes I'll say as a forward gain. Right? So let me look at the other two quickly. So now if I look at S22, that will be V2 minus by V2 plus when V1 plus is 0. So basically I'll have to apply signal here, right? And I want to make sure that V1 plus is 0. So when I launch signal here, this goes. I don't want V1 plus to come back. So this guy must be terminated with Z. Okay. And this is the fraction of the V2 plus that gets reflected. So this is the output reflection coefficient, right? And the last guy is this guy S12. So what is S12? V1 minus by V2 plus. When V1 plus is 0, or I put Z0 at port 1. So again here it means here what it says, V2 plus is launched. I want to find what leaks to the first port. So this is basically the if you call it a reverse gain or a reverse isolation, right? Because in many cases you don't want things from the output port to leak to the input port. You want this in many cases to be as low as possible. Okay. Good. So the bottom line is this. In practice, although in theory, although this y, z parameters are all nice, there are severe practical limitations in actually measuring them, right? And couple of them are the fact that you can't ensure a proper short circuit or open circuit at all frequencies, and because of these multiple resonances, there is a high chance for things to become unstable. So that's what led people to invent a new set of parameters, which is S parameters. Okay? So it is not like people invented something new to make you study more and to ask more questions. Okay? There is actually a reason behind doing this. Okay, so let's say I have this two-port network. I don't have to draw. So I know S parameters. That's basically this, right? So let's say if I were to find y parameters for the same two-port network, do you think these y and S parameters are related or not related? Huh? Should be, right? Because it's the same two-port network. And let me show how you do that so quickly. Y parameters says what is the current in terms of the voltage. I'll just say it's IC so that don't confuse with identity matrix. Okay, and you know that total current is, or let's say what is the total voltage? It's V plus, this V minus, and the total current is 1 over Z naught. Okay, so how do you know? Okay, so now I want to find y parameters or the y matrix from S. How do I do? Yeah, so I can basically try to put this fellow here. So what I have is by Z naught V minus to be y times minus, and I know the relation between V minus and V plus. So this is going to be I minus S times V plus I plus S times V plus. Okay, fine, right? Okay. So what is y then? Yeah, from this tell me what is y matrix. 1 by Z, I have this term.
I plus S equals to I.
Huh? Okay. And you guys know that for y parameters, if the network had only R, L and C, y12 was y21, right? And you know the relation between y and S parameters. So take it as exercise and try to find what this means, right? See, now you know S parameters is basically what? S11, S12, S21, S22. Use this and substitute for S. Try to find what is y12 in terms of S parameters, y21 in terms of the S parameters, and basically these two are equal. So you can find that actually this gives these two are also equal. So let me probably do a couple of examples. So let's say this is a two-port network. So okay. And I want to measure the two-port parameters. So again, assume that you have cables with characteristic impedance Z0. Right? So let me just do for y11 and let me mark the voltages first. This is V1 plus, V1 minus V2 plus V2 minus. What is y11? What is the ratio? Okay, let's look at it. Sorry, not y1, S11, right? Sorry, yeah, S11 is, it's basically the input reflection coefficient. Okay, so it just says the fraction of the forward wave that gets reflected when you have put Z0 at the second port. So at the second port, now I'll put Z0 and I'm going to launch some signal here. Fine. Okay, so now if I have this kind of connection, what is the looking in impedance? It's Z0. So basically I can simplify this guy. To be this. Okay, and now what I'm interested is to find the reflection coefficient, right? I mean, this again, if you were to draw a single-handed version, you will have just one cable, right? This is ground, let's say. This is V1 plus, V1 minus. So what is V1 minus in terms of V1 plus? Yeah, it's basically the gamma L. And what is gamma L? It basically depends on the looking in impedance, and that you guys know, right? This basically these two guys. Let me write it maybe. Zn is, what is Zn? R3 plus Z0 parallel R2 plus R1. So S11 is basically this Zn minus Z0. Zn plus Z0. Okay. So next, let's try to do S21. So S21 is basically the forward gain that says if I launch V1 plus here, what is the wave that goes here? So I need to find the relation between V2 minus and V1 plus. So this is V2 minus by V1 plus, and this is done. Okay, again, so now if let us say this is the voltage V2, right? The total voltage V2, what is that in terms of the reflected and forward voltages? Huh? It's only V2 minus, right? I mean, ideally this is the total voltage, but we have actually matched this guy here. So V2 minus goes, but nothing gets reflected. So the total voltage is V2 minus. Okay. So again, I will simplify this guy by replacing it with Z0. So the total voltage V2 is basically V2 minus. Okay. And again, let us say this voltage is V1. What is V1? Plus V1 minus. That's basically, I mean, I know the relation between V1 minus and V1 plus. That is S11 in terms of S parameters, right? I mean, for the same network where the port 2 was terminated with Z0, I know what is the relation between V1 minus and V1 plus. So I can simply use it. So this is basically 1 plus S11 times V1 plus. So if this is V1, if this voltage is V1, what is V2? I mean, you know that resistor divider thing, right? So it's basically R3 plus Z0 parallel R2, that is this guy. So basically you will have first the division between this guy and R1. So R1 plus R3 plus Z0 parallel R2 times, that gives me this voltage. Then you will have division between this guy, okay, times V1. And I know V2 is same as V2 minus, and V1 is same as this one times V1 plus. Now we have the ratio V2 minus by V1 plus. Okay. Similarly, you can, I mean, okay, so this is S21. What can you say about S12? Same, right? I mean, I didn't do it, but you tried. I mean, from this, you actually try to do it yourself and convince that these two guys will be equal if y12 is equal to y2. And y12 will be equal to y21 for what kind of networks? For linear RLCs. Okay. Okay, so let me do one more example. So let's say here, this time the network is a transmission line. It's a characteristic impedance, same as the reference impedance, right? In all these cases, reference impedance is Z0. So this is the two port we have. So again, now we'll have a cable. This is the external cable that we'll be using. So let's say I want to find S11, that is basically V1 minus by V1 plus. When I put the reference impedance at the second port, so I put the reference impedance here. So at this end, the voltage is V1 plus, V1 minus. What is S11? Okay, what is the looking in impedance here? Of wait. Huh? Looking in impedance is Z0. So now it looks like I put a Z0 here. So what is the looking in impedance? That is also Z0 now. Okay. So now here I have a transmission line Z0. Here Z0. S11 is 0. So let's say we'll find S21. S21 is basically the forward gain, that is Z0 at port 2. So this is basically V2 plus, V2 minus. So I apply some voltage here, I mean a forward wave is launched. I want to find the forward wave in this. I mean, yeah, it cannot be exactly equal, right? It's a delayed version. Okay. So, I mean, now we'll have to do it in frequency domain, right? So, V2 minus of S is times S tau. Okay, so this is S21. S21 is e power minus S tau. That will be same as S12, right? Because again, it's a transmission line, it has only L's and C's. So, what can you say about S22? For finding S22, I'll basically put Z0 here, apply some signal here and find what gets reflected. What is it? 0. I mean, basically it's the same line, right? Whether I look from here or here, it's basically same. So the matrix, if I write, it looks in a nice form like this. Okay. Cool. So now let me take another example. So let's say this is again a transmission line. But the characteristic impedance is Z1, whereas our reference impedance is Z1. Okay. Again, we do the same thing. This is the network. Now we'll be putting cables here, and these cables will have a characteristic impedance Z0. That's our reference impedance. So here again I'll have the same cables. So now let's say we want to find S11. This is V1 minus, sorry V1 plus, and this is V1 minus. Actually, let me mark it clearly. At this end, the forward voltage is V1 plus minus. And S11 is basically V1 minus by V1 plus, and I put Z0 at the other port. So I'll go ahead and put Z0 here. What happened? Oh, it is running. Let it go, it's okay, we'll see. Yeah, so this is fine. This is the setup. So now the forward voltage at this end of the cable is V1 plus, So can you comment about the forward voltage at here, at maybe this point? Okay, I mean, first of all, is everyone clear that the same forward voltage cannot be here, right? Because here the total voltage is sum of these two, right? The voltage has to be same at these, total voltage must be same at these 2 points, okay? But if this is V1 plus, the forward current is V1 plus by Z0 at this end. But if the same forward voltage goes here, so if this is also V1 plus, but this will say that the forward current is V1 plus by Z1. That's not possible. And again, that's happening because this has a different characteristic impedance than this guy. Okay. So here I will have a different forward voltage and a different reflected voltage. Is that okay? But I mean, the total voltage is same. That is V1 plus plus V1 minus will be same as this guy. Similarly, the current here, total current will be same. So what is the total current at the end of this cable? By Z0 minus V1 minus by Z0. So this will be same as Z1. Okay. And now if this is Vx plus, at the end of the line, what is this? E power minus S tau. This will be Vx minus e power S tau. So the looking in impedance here is what? Z0. But this impedance is Z1. Oops.